Example 10.15. Here we have two blocks M1 and M2 attached by a cord, light cord, through a pulley with a moment of inertia I. When I say we have I, so we have a weight. In this case, the tension on this side is not equal to the tension on this side. So we can say here directly, here we have T1 and here we have T2. Initially, this is the initial position of M1 and the initial position of M2. We release the system without initial velocity. M1 get up a distance h, M2 moves down a distance h. I need to calculate the velocity of M1 and M2. You know here M1 V1 equals to V2 equals to V. Why? Because it's inflexible chord. Okay, in this case I have the same velocity. I need to calculate V and omega at the time t. So at the time t, find omega of the pulley and V of the mass M1 and M2. Okay, you know here, first of all, you have to precise the direction, the positive and the negative. As you see here, in general, I take the positive direction is anti-clockwise. Okay, so here you can say the positive is anti-clockwise. Okay, for example, here is a positive. Up is positive, down is positive. You have to take the same direction, plus, plus, plus. I know the system is moving up in this direction, but I prefer to take always the positive direction, the anti-clockwise, like this. Up, positive, down. This is the positive direction. And I need to solve the problem with respect to these notations. First of all, for M1 and M2, M1 and M2, we have a translational motion. So we have to apply summation of F equals to MA. For the pulley, we have a rotational motion. So we have to apply summation of tau equals to I times alpha. Okay, we can apply this one, and we can get a relation between A and alpha to solve the value of omega and V. Let's start with, before the calculation, let me explain a very important point. If I ask you to calculate, for example, alpha or A or T, for example, T1 and T2, as you see here, we have T1 and here we have T2. If I ask you to calculate T1, T2, A alpha, you can use these two relations. Okay? If I ask you to calculate omega and V, we don't need to take each object alone. We can go directly to the conservation of mechanical energy. It's better. As you see here, we don't have friction. Between the axis and the pulley, we don't have friction. Between the cord and the pulley, we don't have friction. So we can say directly delta mechanical energy equals to 0. It's easy to use this equation to calculate the velocity. Maybe later I can ask you to calculate T1 and T2. We can use these two relations. Okay? Here you have to know we have two choices to calculate to solve this problem. Delta mechanical energy, or the summation of F and the summation of tau. Let's start with this one. You know, this one is the initial velocity, initial position of M1 and M2, and this one is the final position of M1 and M2. So here, as you know, we can take here as a reference, M1 initially has 0 height, and listen, M1 moves from this point to this point. You take the lowest position as a reference, okay, here. And M2 will move from this position to this position. Also, you can take the lower position as a reference. I don't need to take the same reference for the two objects. So we can say mechanical energy initial equals to mechanical energy final. Kinetic initial plus potential initial equals to kinetic final plus potential final. Okay, initially the system was at rest, so equals to O. Potential initial. Let's see. M1 initially has 0 height, so 0 we can say M1 G times 0 plus M2 initially has H height, so we have M2 G times H equals, you know, here I take all the system. I take all the system. So, you know, here initially the pulley is not moving. The initial height and the final height is the same. So the potential energy is the same. Okay, we can say for the pulley, this one is the reference level without height. So the height of the pulley initial and final equals to 0. Okay, this is about the pulley. So about the potential energy, we have only for M2. The kinetic final. M1 is moving up, M2 is moving down, and the pulley is moving with a pure rotation omega. So M1 and M2 have a translational kinetic energy, and the pulley has a rotational kinetic energy. We can say kinetic energy for M1 and M2, we have half M1 V square plus half M2 V square. This is the translational kinetic energy of M1 and M2. And we have here a rotational motion, rotational kinetic energy of the pulley equals I over 2 times omega square here of the center of mass. Why? Because you know here I equals to ICM plus MD square. ICM is given, and D is the distance between the X and the center of mass, equal to 0. So we have only ICM. We can say directly ICM. Okay, this is about the kinetic. What about the potential? The final position, M1 has a height h. So we have M1 G h, and M2 has finally 0 h. So we have 0 potential. Here we have a simple relation. Look, this one equal to 0. H, okay, is given. I need to calculate V and V, but I have omega here. You know, here we have a relation between V and omega. You know, this point here, the chord is passing through this point. The velocity of M1 equals to the velocity of the point A, because the chord is passing through the point A. So the velocity of the point A equals to the velocity of M1 equals to the velocity of M2. Okay? Okay, because if we have a rotation, as you see here, the velocity of VA equals to R times omega. Here we have R, and here we have omega. So we can substitute the value of V1 and V2 by R omega. So we can write M2 GH equals to V square M1 over 2 M2 over 2 plus ICM times omega square equals to V square divided by R square. If you want to calculate omega, you have to substitute the value of V equals to R omega. If you want to calculate V, we can substitute the value of omega by V square by V divided by R. Okay, here you can calculate R or omega. We have a relation between them. Plus M1 G times H. Okay, here we can calculate V square of the value of V easily. We have the value of M2 of G of H. Also, I give you the value of ICM. Let me clean. We can write finally V square equals to M2 GH minus M1 GH divided by M1 over 2 M2 over 2 plus ICM over 2 divided by R square. Here we can simplify the relation. We can take half as common down. We can take GH here and 2 will be up. Inside we get M1, M2 minus M1. And here we have M1 plus M2 plus ECM divided by R square. This is the, if I want to calculate V, I have to put radical. This is the value of V. Okay, now, for example, I can add, I need to calculate the angular speed of the pulley. So we can write easily the relation between V and omega of the pulley equals to R times, no. Here we have V equals to R times omega. Omega equals to V divided by R. Okay, we can substitute the value of V here. We get the value of omega in radian per second. Okay, it's easy. So it's equal to 1 divided by R times the value of V. Okay. Okay, I can add a simple calculation. I can ask you to find T1, to find T2, for example, to find A, to find alpha. Okay, you can calculate any one of these values. For example, I told you, if you want to calculate T1, T2, A, and alpha, you have to apply the relation of the Newton's law on M1 and M2 equals to F equals to MA. And also for the pulley, you can apply summation of tau equals to I times alpha. Okay? Okay, let's calculate these values. We can add here one problem. Find T1, find T2, find A, find alpha. Alpha for the pulley, A for M1 and M2, and the tension. You know, here we have T1 and T2. Okay, let's start with the system. I told you I take the positive. The positive is always anti-clockwise. The positive. This one is positive, and we can do like this. Positive. Okay. For the mass M1, here we can take only this. Okay, like this, or at any position for this one. What we have? Anyway, for the object M1, we have summation of F equals to M1 times A. F, we have mg, M1 times G in the positive direction. We have plus M1 times G. T1, I take the system. T1 is up in the negative direction. Minus T1 equals to M1 times A. Okay? You know here, V1 equals V2 equals to V, and A1 equals to A2 equals to A. An extensible chord. Okay? This is the first equation. Relation between T1 and A. Let's take the mass M2. We have M2G is in the negative direction, it's down, it's a negative direction, minus M2G. You know, this is a positive. And T2, look, I take this system, okay? This system, here we have T, and here we have mg. Okay, M2G in the negative and T2 in the positive equals to M2 times A. This is the second relation between T2 and A. So equation 1, equation 2. We have to find also a relation between T1 and T2, because for these equations we have A unknown, T1 is unknown, T2 is unknown. So we have 3 unknowns for 2 equations. It's not enough. We have to find another equation to find the unknowns values. We take the pulley. Summation of tau equals to I times alpha. Okay, for the pulley, let's clean. Like this is a positive direction. Here we have T1, here we have T2, here we have Mg and the reaction. You know, tau of Mg equals to tau of the reaction equals to 0. Why? Because pass through the axis. Okay? So we don't have tau. What about T1 and T2? You know, T1 turns the pulley in the positive direction. It's down, down, in the positive direction. So we can write directly plus tau of T1. And T2 pulls the pulley in the negative direction, down, because here we have the positive. So we can write minus T2 equals to I times alpha. Okay, here we can put directly the absolute value of tau, which is equal to T1 times R minus T2 times R equals to I times alpha. Okay, I can write here T1 minus T2 equals to I times alpha. You know, we have a relation between alpha and A. Look here. As before, as V for this point, the point A, the A tangent of A equals to A1 equals to A2, because the curve passes through this point. So we have the same acceleration for this point and the mass m1. We can say directly A, you know, A of the point A equals to R times alpha, the relation between A tangent and alpha. This is the relation between them. So we can write directly here alpha equals to A divided by R. Here we can eliminate alpha here, and you can write A divided by R. Okay, as you see here, we can calculate T1 from the first equation. We put it here. We can calculate T2 from the second equation. We put it here. And we can calculate A from this relation. Okay, now it's easy, the calculation. Okay, this is the equation 3. From equation 1, we have T1 equals to M1G minus M1A. From equation 2, we have T2, which is equal to M2A plus M2G. We put 1, or we can say we put T1 and T2 into equation 3. Okay, here we get R times T1 equals to M1G minus M1A minus T2 equals to M2A minus M2G equals to IA divided by R. Okay? We can calculate A. Here we have M1. Okay, we have to put A outside. Here we have R M1G minus R M1A minus R M2A minus R M2G equals to IA divided by R. So we take A common. We can say A equals to R M1G minus R M2G divided by I divided by R, okay, plus R M1 plus R M2. We can, I think, okay, this is the value of A, okay. Anyway, I don't want to continue here. Just let me see. Here we have alpha. Okay. Here you can put the value of A. We can say equation 4. So we put the value of A into equation 1. We get the value of T1. We put the value of A into equation 2. We get the value of T2. And we can find alpha. How? We can say A equals to R times alpha. So alpha equals to A divided by R. We can calculate it. Here you have to know to find, I repeat, to find A, alpha, T1, T2, you have to apply Newton's law and summation of tau equals to I alpha, M alpha. If you want to calculate omega and V, you can apply the conservation of mechanical energy directly. Thank you.